Thank you, Elke. So first of all, yeah, now you see that finally the slides have changed. We have the OpenModel slides. So we're moving a little bit farther. And I also would like to first just point out the names of Louis Ponnet from EPFL and Kasper Andersen in SINTEF, who have been two of the main people developing what I'm going to show today. So what I'm going to talk about, I'm going to talk a little bit about something called execflow. And you can see here, this is the link to execflow. This is an extension of the AIDA workflow manager, which is a very advanced workflow manager for computational research and modeling, and it's developed by EPFL in the group of Nicola Marzari. And in OpenModel, it has been developed further, and new parts of it have been developed in order to be able to get a semantic description of the data that goes in and out. So what we're doing is that we're using OTAPI that you have seen all about, and we have even further developed it. It's SINTEF in both projects, and also we're using Delight as the interoperability framework, at least an example I'm going to show now. And what AIDA gives us is the possibility to use an advanced workflow manager, and at the same time it gives us which means that we can use all the AIDA plugins, all the things that they have to really run advanced computational software, attachment to high performance computing centers, etc. And it also gives us full provenance of our workflows or our data. What I wanted to do, since this is called a workshop, is I wanted us to have a workshop and actually do something, but this is a PowerPoint workshop, so you will see it on the here, but in the next slide you will see that that this is also something that you can try at home if you want. So what is your hat right now? I'm trying to describe execflow to persons that are interested in advanced workflows and maybe not want to develop them, but might want to use them or have someone in their companies use them. And I'm just going to show you how this is implemented in execflow. So what we have seen already is the use of partial pipelines. The partial pipelines, they document the data that we want to get, our data sources, and they document our data sinks, the data that we want to, that we are generating and provide and put somewhere. And what we want to do is to then use this further. So I'm not going to talk very much about pipelines, but it's important to know that we're using them here. So what is our use case? And okay, here I thought it was a website URL. Then maybe it's the next one. But I want to show you in a use case, an actual use case. And this use case is a very simple one where there's a person asking what is the density of water? And of course, our answer is not go to a textbook. It is go and calculate it. So there's a guy here answering, yeah, you can run a simulation. And this person says, oh, that's a bit hard. I don't know how to do that. But we have OpenModel. Now, OpenModel has, at least we're developing, a very important part, which is called OntoFlow, which is based on the OntoKB, OntoRec that you already saw before. And it's, of course, developed by Luca and his group. That one is, in our experiment, or in this example, has already done what it should do, which is to generate the workflow description. So now we're just showing the workflow description as if it was generated by execflow. And the question, what is the density of water in this OpenModel platform? We can translate to this, please make an instance of this data model. This is the same type of data models that Jesper was showing before. It's very simple. It has only one URI, and it also has one property, which is the water density. In a real example, we would probably add the temperature and the pressure and maybe some other parameters. So how does our workflow look like? We have this line here, which you see is comprised of several arrows. there are the lila arrows, and the lila arrows are the steps in the workflow. And then inside some of the arrows, there are some blue arrows, and the blue arrows are the pipelines or the partial pipelines that are put together into forming a whole pipeline. So I will go through each of these steps. Here is actually the example that is publicly available on the OpenModel. Also, ExecFlow is, as of last week, publicly available, so everyone can run it. So this is possible to run. As you might see, if you look carefully, this is not on the main branch of the public, but if you're interested, please just write to me and I'll help you. So the first step is this one here, which is to fetch the data that we want and generate our input. A little bit to the back again, I forgot to say one thing that's a little bit important for you to follow, and that is that first we generate some input and we give it to a program called Moltemplate. Moltemplate is a program that generates input for the real simulator, which is LAMPS. So these two programs are very intimately connected and they run just one after the other. But that's what we're going to do here, is to just run get data, run Moltemplate, generates input files, LAMPS runs the simulation, and then we have a post-processing tool, which is our little simple tool, but it's pretended to be a more advanced post-processing, and then we document the final data. Then I think I can go forward. So the first one, we have to fetch data and we have to generate the input as we want it to the Moltemplate. In our case, we are reading them from Excel files. You can see here to the left. And we have two partial pipelines because we need data from two different sources, which are these two Excel sheets. And what is important here, just to remember, is that it looks on the top here that we're running them in parallel and then going in. What is important is that in reality, we don't run them in parallel unless we start making parallelization of the software. We haven't done that. But what is important is that we make sure that all the partial pipelines that need to fetch our data, run before we use the generation partial pipeline. So basically, we fill up our library, the library is filled up, and then we can use our pipeline that fetches the data. Now, back to this bigger line, the whole line, and we see that we actually have the workflow description, which is the declarative work chain. We call it the declarative work chain, is just a YAML file, and we have a number of steps. And for each of the lila arrows, there is one step. So we have the workflow. It's difficult to. Yeah, the first one is the pipeline. Then we have an exec wrapper, which I will explain what is afterwards. Another one, exec wrapper. Then we have something called a calc job, which I will also explain later. And then we finalize with the pipeline, the final pipeline that generates the data that is coming out. How do we run the pipeline? So I showed before that it's basically running two partial pipelines, filling up a library, then running the final pipeline that generates the data. In our ExecFlow or declarative work chain file, we actually have to ask that we run a pipeline. Then we have to give it a file. That is the pipeline. We could also put them one after the other. It don't have to be only one file, but we can have several. And then we have to make sure that we do this conversion between, and here it's called CUDs, but for those of you that know us, Symfony Core, we're not actually talking about those CUDs, we're talking about open data models, Delight data models. But we could probably use a different, we just interoperability system as well. So we have to do this conversion, and that's a special function that converts what we are getting from the pipeline into an AIDA data node. That is, this is difficult. That we can use afterwards. Okay, I'll try to stop doing this. It's a bit too complicated for my fried brain at this hour. So, going on to the executables. So AIDA has a lot of capabilities. You can write advanced plugins that you can use to run your simulation software and make sure that you have all the prominence on all the small parts of your software. So if you're running QM calculations or DFT, you can put in all the data on each different functionals you want to use, and I mean, everything. If that is a bit too difficult, and maybe the first step it is difficult, you can just run an executable. And in this, so that's what we're doing here. We are running a program called MolTemplate, and here I've called it mock MolTemplate because I want to have a mock example where you don't have to install anything. And basically the only inputs that you have to document there are the input files or the arguments, and what the files come, what is being outputted and that you want to use later. So you have to make sure that we give it to the command, we have to give it the arguments, then we have to tell it if these arguments are files, we have to specify which files, and then we give it the outputs. That was MolTemplate. Now, since MolTemplate is so intimately connected to LAMPS, there's no reason to document the data coming from MolTemplates in a manner that with the partial pipelines. We can just run the LAMPS directly afterwards because the output files are just shipped over directly. And so that's what we do. We actually run another exec wrapper, where we just use the executable. Now that's LAMPS that's running, mock LAMPS. It doesn't actually run a simulation. You don't have to wait for 10 minutes, and you can wait for 10 seconds. Then you have the arguments that come in here. You can also see that you can put in arguments that are not files or anything. This is just a string, the top one. But then the next one is an in that has to be resolved in some way, and that's resolved here in the files. Furthermore, we have a lot of other files that have to be made available. And they are not in the arguments, but if they need to be made available, you have to pick them up here. So you have to tell them which files it should find. Now it's a little bit strange here. You have this CTXs, strange things. And then I will show you afterward. The reason why we have them is because we have to be able to transfer our data nodes, the AIDA data are put into something called data nodes, from one step to the other. And that's what we see here, is that after having run one step, this step is it's the LAMPS step. We get some outputs. So these are the log.lamps, output.log, and output.dump in our case. And what we do is that we make this post-processing part in the declarative workchain, which basically is just making a dictionary of key value pairs. And then we end up having in our local context, in the workflow that we're running right now, we have access to the things that we put in there. And that means that in this case, we're putting context, current outputs, output log into the context, to context. And then in the next job, we can pick it up again. So that makes sure that we can take one thing from each, from one step to the other. So then we have the final part, which after having run the LAMPS, we want to get out some data, because otherwise we just get some files out with lots of numbers. What should we do with them? And in our case, we're interested in the density, and there is a column with the density because we have actually put in a lot of water into a box, and we want to know what is the density of this of the water in this box after simulation. And here we can actually run instead of running an executable, we made our own AIDA calc job, which is, could be compared to a plugin, and we can then use that directly instead of having to use the executable. So we can mix and match plugins as we wish. Finally, we put this value that comes out here, which is the number, the density. We take it out, and then we have the run a pipeline that generates the output file or the output, and we get this density number that we can use. The final output, then we again have to do this kind of conversion between AIDA data nodes and our data models now in the reverse direction. And then we have to generate our data as we wish them. Here we have another partial pipeline function where we actually generate the data as we want them. And what we do is we want to dump it as a YAML in this case. These commands to the left here are the ones that I wanted you to use after having run this on your computers to actually go into AIDA and check out the values that you get out there. But that we can do if you write me an email. I'll help you with that. So what is actually semantically described here? Actually, what is really semantically described are these things with the pipelines. And what is in the middle here is kind of a black box. So that means that the output here, we can use it later, but the output from lamps is a little bit difficult to use unless we are know how to access them inside AIDA, which is possible, of course. But what we can do if we want to make them available in a more direct manner through the OT-API pipelines, we can add a new pipeline in between these two steps, which documents the output files. And then we could just use exactly the same declarative workchain up to including lamps. And then instead of using this post-processing here, we could have a different post-processing that we want to make, which, for instance, there could be finding the radial distribution functions or something else. So now, please run the example. Good, everyone run the example, very nice. And of course, you can see that it was very quick on my machine as well. What I did ask for was this one here. Like, this is what I showed at the top. The woman wanted water density. This is translated into this data model. So that's important. You have to be able to document what you want. Jesper has already shown that previously. We have in the partial pipeline, we are generating the output and storing it somewhere. And as you see here, that's just a file on my local machine. And what this one is actually here, and is this here. And you can see that you actually get the output as a density 1.044. It's not so far-fetched. And finally, once you have run this one, you can actually get a picture of the provenance graph. These are all the steps that are documented in AIDA, and you get full knowledge about what has run when, what has used which part of AIDA, and you end up with this really complicated graph, which is then possible to make use of later, and you can know exactly where your data came from. That was it. I feel fried. I hope you don't.
Thank you very much, Francesca. Many thanks. It was great to see the two projects using each other and running together and doing cooperation together. And Sasha, is there any comment from the colleagues here? Faja, would you like to come here?
I'm curious regarding the provenance graph that's being produced by at the end. What kind of information that's contained inside? Is it also, I don't know, can you configure like what kind of information that you want to take from each of the process, how deep it is and so on?
Figure that when you make the plugin.
Mm-hmm. So you create.
For instance, if I go a little bit back here, I was back.
They don't like it. Oh, it's N.
Okay, that did not work.
Yeah. Okay. Yes.
Oh, there it is. Yeah. So this one to the left here.
Yeah.
That's the provenance graph of the first pipeline.
Okay.
And the reason why it looks so complicated is with all the steps in the pipeline, the plugin that we have made for the pipeline has made sure that we document every function in the pipeline. But you can, of course, make something that is less verbose or that has less information, like this, the execute shell that just runs the executable, and that's it. And those are those two that you see up to the right here. With this like pink square. It shows you which are the input files and the output files, but not much more because we haven't told it. We haven't made a plugin that has all that information. So that really depends on what you want with the how detailed you make your plugin. But if you want to run, for instance, Quantum Espresso, which is well developed in AIDA, then you will be able to get a lot of information about all your whole DFT calculation. And the final one there is then the last pipeline that generates the density.
Cool. Thank you.
Thanks, Fajar. Any more question here from the colleagues, comments? Maybe I have a short one. I was just looking at your pipeline, and we have lumps, and you say that we can easily or somehow we can add some output there or a step there in between the pipeline. But if we want to change in the pipeline and not know some customer using GROMAX or some paid molecular dynamics package, can we also?
Yeah, so that's the whole a bit of the idea with these pipelines is that if we go back to the library drawing.
There, yeah.
So let's say that, so this is a dynamic simulation, and what you have here is you need the temperature and pressure, and then we have lots of other variables that you can put in, right? And I asked for the first slide. But those, if you put them in there and then you generate, instead of using, this one could say generate lamps or molten plate inputs. If we rather make a pipeline that says generate GROMAX inputs. And if this is enough data to run that GROMAX, then you have it all. So you don't have to change the full pipeline.
The full
partial pipelines there documents the input data that we want to get. What is our data sources? This one documents our data sink, which in our case, right in this small pipeline, is molten plates.
Okay.
So we make the each partial pipeline documents one data source or one data sink, and then we mix and match as we wish.
And for instance, I have a topology independent of the input file format, and then I can take this topology and then just format into the format that of the other.
Format to this common language, the data models and ontology. Without ontology, then we can run into troubles. But if we need mappings to the same ontology, unless we all speak the same language at the data model level, we can do that as well without ontology, but it's better to have mappings. And then we can put in the next one as we wish.
Even if it's a paid product like the one that Siemens has, the Koji or any other one would be the same. They also need only input file topology. Some have this.
Something that is not known to us, they have to
because we cannot capture it.
They can't touch it, but it's defined to possibly do that.
Fantastic. That's very great. Michelle, if you would like to come, you have a microphone, I think, but you can come here. You can come.
Already works. Yeah. Thanks. So thanks for the talk. I would like to ask now, imagine you want to submit a paper. Then they nowadays ask, where do your data come from? Would you be able somehow to send them this AIDA provenance graph and they are happy?
And most likely.
I guess I couldn't show them that figure, but of course I can give them the database and the provenance graph in a text file, and then it's there, of course. But as long as it's open,
And it's even better for the ones who afterwards take the paper and want to try. That normally we sometimes do take some force fields from a paper and so on. It's much easier to take the
so of course the advantage here is that AIDA is open source, OTAPI is open source, all of the things there are open and available to everyone. But as soon as you run into running a Gaussian example, then you have to pay.
And then, yes. Any more questions? No, if that's not the case, I would like to say many thanks to Francesca for the talk.